a vast room full of people, all trying to describe a glowing object hidden in the shadows. If you pull just one person aside and ask them what they saw, you are taking a massive risk. Their view might be blocked, or they might be standing at a weird angle. Relying on their single conclusion is dangerous. In machine learning, we face the exact same problem when we rely on a single predictive model, like a decision tree, to analyze our data. A lone model is incredibly brittle. This scatter plot demonstrates the trap. The model either memorizes the noise in your data perfectly, or it is so rigid that it completely ignores the underlying pattern. How do we trust an AI system if the individual models powering it are practically guaranteed to be flawed? We stop looking for one perfect observer. Instead, we use ensemble methods, combining the guesses of multiple weak models to form one highly accurate conclusion. There are two distinctly different ways to build that consensus.
The first architecture is called bagging. It operates on a strategy of strict parallel independence. Here is resampling with replacement. The system takes the original dataset and pulls random samples to create slightly different versions. Some data points are duplicated, others left out. It's like putting each observer in a separate room, giving them different evidence. From there, each model is tasked with making its own prediction at the exact same time, completely isolated from the rest of the group. The most common engineering application of this parallel method is a random forest. To get the final answer, the system simply takes all the predictions from those noisy, chaotic trees and averages them together. By averaging a large number of independent, flawed models, the random noise cancels itself out, leaving a single, stable consensus. The second architecture is called boosting. It completely abandons that independent parallel approach and builds a sequential, hierarchical chain. Here, models work sequentially. The first guesses, and the system flags exactly where it failed. The second focuses almost entirely on the first's mistakes. This repeats. Every subsequent model tackles the hardest problems its predecessors couldn't solve. We typically see this deployed as boosted trees, using algorithms like AdaBoost. Boosting systematically strengthens weak learners. It takes a chain of poor guessers and forces them to iteratively correct past mistakes until they form a highly precise predictive engine. Because they both combine models, it is easy to assume bagging and boosting are interchangeable ways to solve the exact same problem. They aren't. Bagging's parallel structure is specifically designed to reduce variance. It tames chaotic models that are overly sensitive to noise. Boosting's sequential structure does the opposite. It is engineered to reduce bias, adding complexity and strength to rigid, underperforming models. This split-screen diagram highlights the stark architectural divide. On the left, bagging pulls models together at the very end to vote. On the right, boosting links them end-to-end to learn from each other. Choosing between random forest and boosted trees depends on whether your raw models suffer from too much chaos or too much rigidity. The reason model averaging works at all comes down to a mathematical principle called uncorrelated errors. If your models make independent, uncorrelated mistakes, the expected squared error of the entire ensemble decreases linearly as you add more of them. The math dictates that their individual errors cancel each other out. It reveals a philosophical rule of ensemble methods. Many observers, judging independently, are rarely wrong together.
This is why modern machine learning contests and massive enterprise systems aren't run by a single, perfect God algorithm. They are run by diverse committees of algorithms, specifically chosen to cover each other's blind spots. But what happens when that committee encounters a problem so complex it requires sending a sharper eye to correct the last mistake, step by step, down a gradient?